The next little section on page 13 is how we can analyse the free energy equation without actually using any numbers. Because some of you might have noticed in the equations we looked at, or the examples we looked at the top of the page, we weren't really actually interested in the actual values for free energy, the fact that this is 130 and this is 750. All we were interested in is the sign of the final answer. We know that something's positive, it's not feasible, but if something's negative, it is feasible. So because we're only really interested in signs for this equation, sometimes you can actually just do some analysis on the equation without really worrying about the numbers and just worrying about positive and negative. So that's what we're looking at here. You've got this free energy equation, and what we go through in this section is analysing all the different combinations of delta H and delta S being either positive or negative, and see if we can come up with some rules about what those different combinations mean for your value of delta G. So it can be a wee bit tricky, this section, just in terms of getting muddled up. So just take it nice and slow and use the explanations trying to help your understanding here. So your first combination is this. So if we imagine for a reaction that the delta H is negative, it's exothermic, and delta S is positive, so entropy increases. If you analyse what that does to our equation, it does these two things. So we're saying that delta H is negative. So we're starting with a negative value in our equation on the right hand side. We're saying that delta S is positive, and if we're just timesing delta S by T, it's just going to be a slightly bigger positive value. So we've got a negative value, and we're subtracting a positive value from that. That's just going to make that negative value a bit more negative. In other words, it's impossible for that delta G value to ever be positive with that combination, because as you increase or decrease temperature, it's just going to adjust how much you're subtracting from this negative value. Again, you might pick that up very quickly, but for some people it might be a bit harder. Another way of looking at it is actually to make up some numbers, this hypothetically. If I take delta G equals delta H minus T delta S, and again, I'm just going to pick really simple made up numbers. If I just imagine that delta H is minus 10, just for example, and if I imagine that delta S being positive, I'd just say delta S is plus 10. So if it's plus 10, T delta S is going to be 10T. So I'm subtracting 10T from minus 10. If you analyse that sum there, obviously I've not got temperature yet, but that doesn't really matter. No matter what value of temperature I've got, I'm always subtracting a value from an already negative value. It's always going to get more negative. And if it's always going to get more negative, it's impossible for that value to ever be positive. It's negative at all temperatures, therefore the reaction is always feasible. Bringing in a wee bit of common sense as well, we know already that an exothermic reaction is favourable and an entropy increasing reaction is feasible. So it's always going to be feasible. There's no kind of scenario where that can't work. So that's our first combination there. Second one is the opposite. So if we say that delta H is positive, endothermic, but delta S is negative, so entropy is decreasing. Let's look at the effects here. So the delta H is a positive value now, and delta S is a negative value now. So if you think about what that does, T delta S is now negative. So the effect of minus T delta S is you're adding a value to that positive value. If you're adding a positive value, because that minus sign is changing that to positive, to an already positive value, it's just going to get more positive. It's never going to end up being negative. It's never going to be feasible. Again, if we have a look at the kind of made up number version again, if I just pick 10 and 10 again, so let's just say delta H is positive, let's call it plus 10 now. And let's say delta S is negative, let's say it's minus 10. So it's going to be minus 10T, which the effect of that is plus 10 plus 10T. So looking at those numbers again, there's no possible combination with temperature, because temperature always is positive, that's going to end up being negative. So if something has a positive delta H and a negative delta S, it's never going to be favourable at any temperature. It's never going to work. Those first two examples are a bit more clear-cut, but it can get a bit more complicated with these too. Because in the final two cases, you've got two factors which kind of contradict each other. In the first one here, well, the third one here, delta H is positive, so it's endothermic, that's not favourable. However, delta S is positive, which is entropy increasing, which is actually favourable. So you've got one factor which is saying a reaction shouldn't happen, and one factor saying that the reaction should happen. So the question is, well, which one wins? Which one is more important? The answer is that it depends on temperature. So let's look at this kind of bar graph version of this kind of analysis here. So we've got delta H as a bar and minus T delta S as a bar here. So let's just make sure it makes sense. Delta H is positive, that's going up. Delta S is positive, so minus T delta S, taking that minus sign in there, will make that negative. So you're basically combining these two bars to give your overall value for delta G. So in some cases, your delta H bar will be taller than your minus T delta S bar. That's going to make delta G overall positive. So in other words, your positive unfavourable delta H value is kind of taking priority over the favourable minus T delta S value here. However, in some other situations, your T delta S value might end up being bigger than your delta H value, making overall negative, delta G making it favourable. The factor that you're changing there to make it either favourable or not favourable is the temperature. Again, this is a wee bit confusing. So at low temperatures, your favourable minus T delta S value is going to be quite small because you're timesing the entropy by the temperature value. And when that value is quite small, your positive delta H value is kind of taking priority there. It's making the reaction overall positive, makes it unfavourable. However, as you increase that temperature value, the T delta S term in your equation becomes very big because you're multiplying by temperature. At a certain point, it'll become so big, it's going to overtake the size of that delta H value. And once it overtakes that value of the size of the delta H value, the overall value for the equation is going to turn negative. Once it turns negative, it's going to become favourable again. So the way we can explain that is a tricky point. I hope that makes sense. So if delta S is positive, then the T delta S term in the free energy equation will always be positive. Delta G is given by subtracting T delta S from delta H. So this important bit here. In this case, the value of delta G will depend on the relative sizes of the T delta S and the delta H terms. If T delta S is bigger than delta H, then delta G will be negative, which is what we get here and is feasible. However, if T delta S is less than delta H, delta G will be positive and therefore not feasible. That's this scenario here. Delta S and delta H are fixed, but the temperature is altered and the temperature will affect the T delta S term. So that's how we control it. We can increase the size of the T delta S term by increasing the temperature, and that will affect the feasibility of the overall reaction. So, summarising that in one kind of sentence, above certain temperatures, the T delta S term will be larger than delta H and allow the reaction to become feasible. So in this type of reaction, where you've got delta H positive, delta S positive, we would say that they're feasible above a certain temperature, once you get this T delta S term being bigger than your delta H term. Finally, we've got the last kind of combination, which is very similar to the third one, just the other way around. Delta H is negative, exothermic, that's favourable. However, delta S is negative, that's entropy decreasing, that's not favourable. So again, we have contradictory terms here. One factor saying it's favourable, one saying it's not favourable. And again, it's going to come down to which one's bigger than the other. Same analysis here. So our delta H value wants to make the reaction favourable. And if it's bigger than my T delta S term, minus T delta S term, it's going to make delta G negative and favourable. However, if T delta S becomes bigger, it's going to make the reaction unfavourable and positive. In this case, because our delta S term is making it unfavourable, it becomes bigger by increasing temperature. So in this case, as you increase temperature, that T delta S term gets taller and taller. That makes the reaction less favourable, and at a certain point make it not feasible to happen. So, putting it into a sentence here, in this case, the value of delta G will depend on the relative sizes of T delta S and delta H. If we have the scenario where T delta S is bigger than delta H, which is here, the delta G value will be positive and not favourable. If T delta S is less than delta H, in this case here, delta G will be negative. Again, the values of delta H and delta S are fixed, but temperature is alterable. So what we would say here, that this reaction is going to be feasible below a certain temperature, because once the temperature gets a bit too high, your T delta S term becomes a bit too positive and it's going to overtake delta H and make the reaction overall positive in delta G. So distilling that all down into one kind of table here, this is kind of what you need to be able to understand. Here are all the different combinations of delta S and delta H. Our first two were clear cut. If delta H is negative and delta S is positive, delta G will always be negative and therefore feasible. If delta H is positive and delta S is negative, delta G always is positive, so it's never feasible. These two ones are the tricky ones. If both delta H and delta S are positive, delta G will be negative when T delta S is bigger than delta H, and that's going to happen when the temperature is big enough for that overall term to be bigger. That means it's going to be feasible above a certain temperature, which we might calculate later on. If both terms are negative, then delta G will be negative when delta H is going to be bigger than T delta S. That's only going to be true when your T delta S is small enough, and it'll only be small enough when you're at below a certain temperature. So it becomes feasible once you drop below a certain temperature. Again, it's confusing. You might need to kind of look at that a few times. It's kind of more logical thinking rather than this learning off. In terms of what question could be asked in that, here's a little example. Generally not really anything in a great amount of detail. So you're given a reaction here. The reaction between citric acid and sodium hydrogen carbonate is endothermic. Using the equation for free energy, explain why this reaction is feasible despite being endothermic. Probably what this should say, which it doesn't, is feasible at a certain temperature. Obviously it's not giving you any specifics, but we're saying in some scenarios it is feasible. So what we're trying to answer is, why would this reaction be feasible despite being endothermic? So if you think about our analysis using what we just looked at above the page, at the top of the page, let's write down what we know already. So our key equation is delta G equals delta H minus T delta S. We're given that's endothermic, so that must mean that delta H must be a positive value. Again, we're not interested in the number, just the fact it's positive. Obviously, we need to know what delta S is. It's not told us immediately, but we'll have to analyse the equation here. We've got two solids reacting to form a gas and a liquid. So it must be an increase in entropy just by analysing the equation. Delta S, therefore, is positive as well. Therefore, if we're asking, like, at a certain temperature, why would it be feasible? We're looking at kind of our table above. If both values are positive, what we're saying is it becomes feasible above a certain temperature because your T delta S term, which makes your reaction negative, is going to become bigger than the positive delta H term. So how we would answer that is that the reaction is feasible as T delta S is bigger than delta H above a certain temperature. And therefore the value of delta G is less than 0, which makes it feasible. So you are kind of using that terminology when you're answering the questions. You're comparing the T delta S term to the delta H term, and that's what they'll be looking for in mark schemes.